electrical engineers will know that a classical computer that we use every day and that maybe some of your audience has helped developing, the microelectronics engineers in particular, are built with the transistors, and when they are used for logic, they act essentially as switches that have two states, a low voltage state and a high voltage state. So that's your zeros and ones in digital logic. And then you build a processor where you have, a large interconnected array of nowadays billions of those transistors, and those are the chips that you use today to do classical computations. So information is encoded in the electrical state of a nanoscale transistor in silicon. It's encoded in a binary mode, zeros and ones corresponds to low or high voltages. And then you do logic operations by having essentially the state of a transistor switching or not depending on the state of another transistor. Okay? A quantum computer is something that retains the binary logic, so it's still based upon zeros and ones, but those zeros and ones are not the high or low voltage state of a transistor, but they are one of the two quantum states of a suitable quantum mechanical object. Okay? So the simplest example one can give is that of an electron that can jump between two atoms. So in my particular research, I work with dopant atoms in silicon. Again, hopefully an electrical engineer will have done in their second year electronics some introduction to what a semiconductor device is and how it works. You take a crystal of silicon, you introduce dopants, which can be phosphorus or arsenic or antimony.
You're primarily using phosphorus though, aren't you?
I am, but also antimony, for other reasons that I can go into if you're curious. But
sure.
So they're N-type dopants. Okay? So normally that dopant will donate, it's a donor, it will donate an electron to the conduction band of silicon. And now imagine you set up your electronic device in such a way that you have two dopants close to each other and just one electron. Right? And you could say, okay, I'm going to encode a bit of information here. I call a 0 the electron on the left and a 1 the electron on the right. Okay? It's a system that can have two options. Another possibility, which is the one that I actually work on, is to use the spin of the electron. An electron not only has a charge, but also has a spin. The spin is the fundamental microscopic magnetic dipole of elementary particles like electrons, protons, and neutrons. And so if I place this electron in a magnetic field, the spin will have two basis quantum mechanical states pointing up or pointing down. So I can call spin down the 0 and spin up the 1, for example. So I could make digital logic that way. But an electron is not just like a transistor. It is a genuine quantum object. So again, think of the two atoms and one electron shared between them. That electron doesn't need to be choosing one atom or the other. It can be in a quantum superposition of being on both. Which again, when you say it that way, people go all crazy. Oh, this counterintuitive real world quantum. This is actually completely logical, right?
It is. Yep.
If you have two identical atoms and one electron, and the system is completely symmetric, which atom will the electron choose?
It's going to choose either.
Both.
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 Yeah, or both.
The logical, natural answer is that it spreads out across both.
Yep.
Right? So I never let anyone get away with saying that quantum mechanics is counterintuitive. It's actually completely logical. You choose both when you have equal opportunities and equal choices. So that means that you can make a quantum bit that is in the 0 and 1 state at the same time.
Yeah.
Okay? Now this is
That's entanglement?
No.
No, that's not entanglement.
That's superposition.
Superposition.
Superposition. Entanglement is the next step,
Yes.
and that's where it gets really interesting. Again, for the benefit of our electrical engineering friends, I quite often get the question from electrical engineers and say, okay, so you have this quantum bit that can be in an arbitrary superposition of being between 0 and 1. Isn't that the same as an analog circuit, right? So if I take an analog amplifier that can have an output voltage between 0 and 5 volts, I can have any range of voltages between 0 and 5 volts. So does that mean I've made a quantum computer? No. And to see why that is, you need to take it to the next step, which is the entanglement.
Right.
So the entanglement is a little bit more complicated, but again, you have to think of the naturality of it, okay? So now let's say that, let me do the example. What do you think is best, the spin or the charge?
Spin.
Spin, okay, let's do the spin.
I'm more familiar with spin.
Good.
I think everyone
Excellent.
else would be more familiar with spin.
Fantastic. Let's do spin, which
Yep.
is my baby. Okay, so now let's say you have two of these electrons close to each other, right? So they have a spin that, in its simple state can be up or down, but it can also be in a superposition, okay? Let's say that this spin is pointing up, right? And really you can take the classical image that you've seen in all your little geography books when you were a kid of the magnetic field produced by the Earth that makes these lines of magnetic field like these that come out of the North Pole and wind around and get into the South Pole, okay? So if you have a spin pointing up this way, it makes a magnetic field that goes up and then winds back down on the side, right?
What scale are we talking about there?
Nanometers.
It's nanometers.
Nanometers,
right.
yeah. Well, I mean, the field spreads out to infinity, but it becomes infinitely small as you go away. So, to have a significant effect, you need to be nanometers close. Okay, so I got a spin pointing this way up. And then I have another spin here, right? So this spin will be subjected to the magnetic field produced by the first spin. So on the side, the magnetic field is pointing down. So this spin will prefer to point this way.
Because that's the lower energy.
That's the lower energy state of the
Yep.
two magnetically coupled spin, right? So this is the preferred orientation for these two. But what if I turn them this way? Then it's equally
It's
enjoyable as
low
before,
energy
right?
state
Because
and
this is
both
now
happy.
making a film. They're both happy.
Yep.
So now, what is the natural quantum state of these two spins that couple through this magnetic interaction? Is it this one or is it that one?
They don't care.
They don't care.
They don't care. It's
They
either.
don't care. It's both. But things are now a little bit more cheeky because now, if I ask you, in that state where they are at the same time, like this and like that, which direction is this spin pointing?
It's going to be always opposite to the other one.
Correct.
So if you know one, you know the other.
Yes.
Hence why entanglement works.
Yes.
Is that correct?
Yes, it's correct. But the point is, this spin doesn't have a direction of its own anymore. So if you ask me, which way is this spin pointing? The correct answer is nowhere.
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 Right.
And if you actually do the calculation, it's really a simple calculation that I teach in third year to electrical engineers. You can calculate very simply what is the expected value of the spin orientation, and it's zero in every direction.
Right.
The spin has essentially evaporated.
So the number pops out as zero for all directions.
For all directions.
Right.
Right?
That's why you can't know.
That's why you have something that a classical system cannot reproduce.
Got it.
Right?
Yes.
So if you now take two analog circuits and you couple them together, you will always have some voltage you can measure at the output of that circuit. Whereas here you can't.
You can't.
Right?
Got it.
So once you get to entanglement, that's where you really see the difference between classical, continuous variables and quantum systems.
Gotcha.
Now, this quantum state here, where they are in the up-down and down-up state at the same time, constitutes a completely legitimate digital code for a quantum computer. Okay? So in a quantum computer with two quantum bits, I can encode 4 different combinations that are completely legitimate. So I can have the down-down, the up-up, the combination of down-up and up-down, where they are opposite to each other. And then there's another one where they are parallel to each other, but they point nowhere in the equatorial plane.
Got it. And that's the extra over basic like digital binary.
Exactly. So these entangled codes, and now if you want to tell me which of the 4 combinations is that set of 2 quantum bits taking, you need to give me the coefficient of each one of those 4 combinations. So to completely describe those 2 quantum bits, you need to give me 4 numbers.
Right.
You need to give me the coefficient of the down-down, the up-up, this one, and this one.
And a number is a piece of information.
Yes.
So you need 4 pieces of information
for
to
2 quantum
describe
bits.
2 quantum bits.
If I had 3, you need 8. If you have 4, you had 16. And so you see that the density of information contained in a set of n quantum bits is 2 to the power n.
2 to the power of n.
Versus n in a classical computer.
Exactly. So this is why you only need, say, 300 odd bits or something as an example. 300 odd qubits we're talking about now. These is a qubit 1
bit.
A qubit is 1 bit.
Yeah.
Right. Is there other words, other terms for like 2 bits and 3? And,
no, but people use the word qubit.
Qubit.
For a d-dimensional system. Right. So you were asking me before, you normally use phosphorus as the dopant where you encode the information. Actually, I also use antimony because antimony, from an electrical point of view, is equivalent to phosphorus. It's on the same column of the periodic table, right? But the nuclear spin of antimony has a spin 7.5, which means it has 8 possible orientation of the spin of the nucleus. So that becomes an 8-dimensional quantum system.
Right.
So you have 8 possibilities instead of 2. So that's a qubit with d equal 8, dimensions equal 8.
Got it. Is there any other advantage to that apart from information density?
Well, for quantum computing, you would. I don't know if I can call it an advantage. It's a difference. One important aspect of quantum computing is how resilient they are to noise.
Right. Okay.
So quantum states are very fragile.
We'll get into that. Why they're cryogenic? Why they're
So if you imagine having, let's say, with an 8-dimensional spin, it's the equivalent of having 3 qubits, right? Because 2 to the 3 is 8. So one atom of one nucleus of antimony is equivalent to 3 nuclei of phosphorus.
Yeah.
Okay? Equivalent, but is different because the way they will be subjected to noise will be different. Okay. Imagine you have magnetic field noise. Okay? So there is a fluctuating magnetic field in the environment. If you have 3 phosphorus atoms side by side, the magnetic field might be slightly different on each one of them. So you have noise which may be uncorrelated. Right. Whereas in that single nucleus of antimony, the noise is by definition correlated. You know, all the levels see, because it's one atom, they all see the same noise.
Yes.
So this can be a bad thing in certain encodings. It can be a good thing in other encodings, depending on how you run it. So this is in the subtleties I probably don't want to go into, but I wouldn't call it better or worse, it's different.
Okay, but for this discussion, we'll stick with the phosphorus.
Let's stick with the qubits, which is the simple thing.
Okay, right. So can we think of a qubit as a storage register? Would that be an accurate, is it a storage element?
It is, with one caveat, that you cannot clone the information. You cannot make a copy.
Can't make a copy, okay.
This is a fundamental theorem of quantum mechanics called the no cloning theorem. You can transfer. So for example, I can encode a bit of quantum information on one phosphorus atom here, and if I have another phosphorus atom next to it, I can transfer the information from here to there. But once I've done that, this one is erased. There is nothing left on this.
Got it. So it's non-volatile as long as you don't touch it.
Yeah.
As long as you don't measure it.
Yeah, but you can't duplicate it.
You can't duplicate